Hello and welcome back. This is the second video about YOLOv4, and in this video we will be talking about the additional improvements besides those that are made on the architecture. So the first improvement that we're going to talk about is the mosaic, and it's part of the Bag of Freedoms. Mosaic represents a new data augmentation method that mixes for training images. So there was a different technique known as cut mix. So you stitch two input images together, and this allows detection of objects outside of their normal context. So data augmentation is a technique used in training in order to improve the performance of a model by introducing some changes to the input so that our model can better generalize to new input images. So in addition, batch normalization calculates activation statistics from 4 different images on each layer, and this significantly reduces the need for a large mini batch size. So what you initially do is when you're training a model, you have to divide the whole training images into different groups known as batches. And if you want your model to perform better, you have to use a large mini batch size. But when you use the mosaic, you stitch 4 images together, and this allows for the model to better localize objects that would not be normally possible by just using the entire image. The second technique that they use is known as self-adversarial training, and it falls under the Bag of Freedoms again, and since it doesn't change the architecture, because we're just modifying the input image so that our model can adjust to other training examples that it hasn't seen before. So self-adversarial training, SAT, also represents a new data augmentation technique that is used to make our model generalize to adversarial examples. So what are these adversarial examples? So for example, if you have an image containing an ox, and then you put it inside a model, and it gives you a prediction that it's an ox with 85% confidence. Then you introduce some small changes, or what are known as perturbation, on the original image, and that will cause the model to misclassify the image. So instead of giving you a prediction of an ox, that it will give you a prediction of a traffic light. So we intentionally introduce small perturbations on the input image so that our model can adapt to changes to our original image. So if you have a function f of x, which gives you a prediction y, then when you introduce a small perturbation of delta to x, then it gives you a incorrect classification y. Then when you add this perturbation to x, it must look like x, and this perturbation can be bounded with epsilon. And the type of perturbations that we introduce can change the image on an L norm. So we can use a 0 norm or infinity norm. So adversarial training is intended to make our model more robust and adapt to adversarial examples. So the images that we generate by introducing these small changes are known as adversarial examples. And the cost function for training an adversarial example is to maximize the delta terms, which are the perturbations that we introduced, and minimize the weights of the network. And the perturbations, as we have talked about before, are bounded. So our cost function is the one which is trying to find the error between our predictions and the original training label. So we want to minimize the error, and the way we do this is by maximizing the perturbations and minimizing the weights. So there are two types of adversarial training. The first one is PGD, and the second one is adversarial training for free. In PGD training, we're gonna be using a mini batch to train our model, and we're gonna train the model k times, and when we do a forward propagation and a back propagation, we're not updating the weights, but we're updating the perturbations to the mini batch. So we're going to have a global perturbations that we initialize. Then by performing forward and backward prop, as we can see on the image on the left side, we go through the network k times. And when we do this, we only update the perturbation and we don't update the weights. And then finally, we introduce or combine the updated perturbations on the original mini batch and train the network one more time. And in this case, we will be updating the weights. So you can see from the image that there will be an overhead of k factor because without updating the weights, we're updating the perturbations k times. And when we train the network, we combine the perturbations with the original mini batch and train the network one more time. In order to reduce this overhead, an adversarial training for free was introduced. So we might have an original mini batch and a global perturbations delta. Then we do a forward prop and back prop. And when we do this, previously we weren't updating the weights, but now we're updating the weights. And at the same time, we'll be updating the perturbations. So using the same mini batch, we repeat the training procedure, maybe in this case, 4 times. So we do forward and back prop using the original mini batch. Then we update the perturbations. Then we combine them with the same mini batch and do a forward and backward prop. We do this 4 times, and then finally, using these perturbations as an initialization for the next mini batch, we use them as global initialization for the next mini batch, and we combine these perturbations together with that mini batch and do the training again. So as you can see, the number of repetitions for the same mini batch can be initialized to 4 or other numbers. And here, since we are updating the weights and the perturbations or the changes to the mini batch, we're reducing that overhead. Another technique that was introduced on the YOLOv4 paper was cross-iteration batch normalization. We have seen previously that batch normalization was used in YOLOv2 and YOLOv3, but a well-known issue for batch normalization is it significantly reduced the effectiveness in the case of a small mini batch. So when we train our model, we use we will have a training set, and we divide the entire training set into mini batches. And if you use larger batch number, then you will get a better performance. But batch normalization's performance significantly reduces when you reduce that mini batch size. So, for example, if you use 32 as a mini batch size, you'll get a good performance. But if you change it to maybe 4 images per batch, then that performance will be significantly reduced. And cross-iteration batch normalization, or CBM, joins multiple recent iterations. So what they did was, in normal batch normalization, we compute the mean and standard deviation. But in cross batch normalization, they also considered mean and average precision from across different iterations. So you can perform normalization on different parts of the network. So normalization is just updating or normalizing the values so that there is a reduced covariance shift. So you can normalize the instance, that's called instance normalization. You can also normalize the layers, also including the channels. You can also do a group normalization. And the rest are batch normalization and CBM. And we can look at them on the image on the left side. So in the video about YOLOv3, we talked about batch normalization. So we have mentioned that since we have features on different scales, let's say when we have an input within the range of 1 and 10, and between the range of 100 and 1000, these two will make our loss function to be an elliptical shape, as we can see on the image on the top right corner. What we want to do is normalize the input features so that our loss function will be smoother and more circular. And this will make the stochastic gradient descent when we want to find the local minima much faster. Because on the original case, we have to move slowly in order to find the local minima. But when the function is smoother, we can find that local minima faster. So in batch normalization, what we did was we computed the mean for the input data in a certain mini batch. Then we computed the variance. Then finally, we normalized the input data by subtracting the mean and dividing by the standard deviation. And finally, we just perform scaling and translation by using parameters gamma and beta. So before batch normalization, a higher learning rate causes a gradient to explode or vanish and stuck in local minima. So when the gradient is exploding, for example, if you have a large learning rate, then it will miss the local minima. And when you have a smaller learning rate, it takes a lot of time to reach the local minima. And batch normalization only adds cost during training, but nothing to do with inference. We only have to do the training for batch normalization, but during inference, since the mean and standard deviation are already computed during the training, and the alpha and the gamma and beta values are already determined, we just do the scaling and the translation by using pre-computed values during an inference stage, so there is no overhead. So it uses the mini batch for updating the statistic of the entire training set. So let's compare the cross-iteration batch normalization with the normal batch normalization. For the normal batch normalization, we compute the mean and variance for a batch, and that's it. But when we use cross-iteration batch normalization, we compute the mean and variance at different iterations, as we can see on the image, from t-2 up to t. Then after computing the mean and variance, we transfer these mean and variance for the next iteration. But since the weights are changing across different time, it's not easy to compute and add the means and variances. So if you do not consider the change in the weights, then it's called a naive CBM. But during training across different iterations, the weights keep changing, and we need to account for the changing weights. So that's covered in the paper about the CBM. So in cross-iteration batch normalization, from the graph on the top left corner, we can see the performance of different types of batch normalizations when we use different numbers of batch sizes. So the green line indicates a normal batch normalization, and when we reduce the number of batch size, the accuracy for normal batch normalization and naive cross-iteration batch normalization drops significantly, and this is indicated by the green and red line. But for cross-iteration batch normalization, which is indicated by the blue line, it remains the same, or the accuracy remains high, even if we reduce the number of batch size from 30 to 1. So that's also shown on the table on the bottom left corner. And during the training, initially the weights and biases change rapidly. So when we consider cross-iteration batch normalization, we say that we need to account for the changes in weights. And initially, when we train across different iterations, the weights and biases change more rapidly. But when our model finds that local minimum, the changes and updates will be more smooth. So cross-iteration batch normalization is not implemented earlier during the training stage, but rather later when the weights are changing smoothly. And the computation cost for cross-iteration batch normalization is 11%. So since it's a bag of freebies, we say during the training procedure, it improves the performance, but it has an associated cost, and that cost is 11% increase in computation and we have a 7% of memory overhead during the training and does not affect the inference. So during training, we have access to the means and variance of at the current time, and we also have access to the weights of the previous time, but we don't know the means and variances at the current for the weights at the current iteration. So that's why we use the formula that's depicted on this image in order to account the mean and variances when the weights, by considering the weights from the previous iteration. And the next is the activation function used in YOLOv4, and activation functions are included in the Bag of Specials. And the mesh activation function was selected for YOLOv4, and experiments show that mesh tends to work better than both ReLU and Swish, along with other standard activation functions in many deep networks across challenging datasets. And if you want more details about this activation function, you can review the video that I made about activation functions. And the mesh activation function is just basically given by the formula the input x multiplied by the tan inverse of the soft plus activation of the input. And the soft plus activation is just basically a natural logarithm of 1 plus e to the power of x. And the mesh activation function can be represented by the graph on the image. And as you can see, for values below 0, it's not suffering from a dying ReLU problem because it has some non-negative values and it's not bounded above, which makes it similar to ReLU. Another technique that was implemented was the IOU loss. We have seen previously about IOU by computing the area of overlap between two bounding boxes to the area of the union. IOU is scale invariant, which means the intersection over union is the same even if we compute it for large and small bounding boxes. But its drawback is that there is no criterion between minimizing the L1, L2, and Huber loss and maximizing the IOU. So on the image that's depicted on the left side, we can see that the loss is the same and it's represented in circle. And there are two bounding boxes. One is the ground truth and the other one is the predicted bounding box. And the box's dimension might change. The predicted bounding box might change, but we didn't use a loss for the IOU in previous YOLO papers. So when you don't use a loss for the IOU, then you don't account for the changing of the IOU when the box keep changing. So it was perfect for overlapping boxes, but it suffers from a vanishing gradient problem due to non-overlapping boxes, since the IOU is 0 irrespective of the location of the two boxes. So what makes IOU loss different from the normal IOU is that the IOU loss is computed by subtracting the IOU from 1, and it's given by the formula 1 minus the intersection between the predicted and ground truth bounding box divided by the union between the two boxes. But it suffered from a vanishing gradient problem because when the boxes overlap, you'll have an IOU value. But when they don't overlap, the IOU will always remain 0. And when the IOU is 0, then there are no gradients being computed in order to minimize the loss function. And if you don't have any gradients, then it's called a vanishing gradient problem, and it doesn't modify the parameters of the network to improve the model. So in order to solve the vanishing gradient problem of the IOU loss, the GIOU loss was introduced. So in the case of non-overlapping boxes, here we can see on the image we have two boxes A and B, and we can consider C is the smallest box covering the predicted bounding box and the ground truth box. So on the image, C is the smallest enclosing box that covers the two bounding boxes. And the GIOU can be computed by subtracting C, which is the box covering the two bounding boxes, multiplied by the union between the two boxes, divided by C again. And the GIOU loss, after we compute the GIOU, when we subtract it from 1, we get the GIOU loss. And when we want to, maximizing the GIOU implies that we are maximizing the IOU when the boxes are overlapped. So the term C multiplied by A union B divided by C is just the area that's not covered by A and B. So if C is the enclosing bounding box, the enclosing box of A and B, then the area which is covered by the non-overlapping boxes is represented by C times A union B divided by C. And when the boxes overlap, that means we don't have this term because the boxes are overlapping, and we don't have the term C times A union B divided by C, and we only have the IOU term. So we need to maximize the IOU in order to maximize the GIOU. And for non-overlapping cases, we need to minimize the distance between the boxes. That means when they are non-overlapping, the IOU would be 0. The only term left will be the area between the two boxes. And we need to minimize it because it's a negative. And when we minimize this term, the boxes get closer and closer, and we are maximizing the GIOU. And when we maximize the GIOU, we are minimizing the GIOU loss because we're subtracting from 1. And the GIOU loss also has its own drawback. And GIOU is a tedious remedy to non-overlapping bounding boxes. And it suffers from slow convergence and inaccurate regression. So, due to the introduction of a penalty term, the GIOU loss keeps expanding the size of the predicted box until it overlaps with the target box. So, as we can see from the image on the left side, the green indicates the ground truth bounding box, and the blue box indicates the predicted bounding box, and the black box is the anchor box. And if we want the blue box to overlap with the green box, what the GIOU loss is doing is changing the area between the two, and the blue box gets larger and larger. And once it reaches the green box, then it tries to maximize the IOU and tries to overlap with the green box. And when the predicted bounding box is on the y-axis and on the x-axis, it suffers from the slow convergence, which means it takes many steps until it reaches the green box. And as we can see, for the slow convergence, it requires up to 400 iterations just to reach the green bounding box. And we also said it suffers from the inaccurate regression. So for the 3 boxes on the bottom right corner, between the red and green box, we can see that the LIOU, the IOU loss, and the GIOU loss remains the same. And if it remains the same, that means it's not learning anything. They are overlapping, but we're not considering the change between the centers of the red box and the green box. They are already overlapping, but their centers are not in the same place. So in order to solve the problem between their centers, the DIU loss was introduced. The DIU uses the Euclidean distance between the center coordinates of the target bounding box and the predicted bounding box. And it's normalized by C, the diagonal length of the smallest enclosing box covering the 2 boxes. So as we can see on the image, we have a green and black boxes, and D represents the distance between the centers of these 2 boxes, and C is the diagonal of the enclosing box between these 2 boxes. And the DIU loss is just computed. The 1 minus IOU term is the normal IOU loss, and then we add an additional term, which is rho squared of B and BGT divided by C squared, where rho squared is the Euclidean distance, the D we have mentioned, between the centers of the 2 boxes, divided by the diagonal of the smallest enclosing box, C squared. And it also has its own drawbacks because it still misses out on the consistency of the aspect ratios. But it solves the problem of GIOU because GIOU has a slow convergence. Here we can see that the red box is approaching the green box much faster than GIOU, because we're just considering the distance between the 2 centers instead of minimizing the area between them, and we can reach the target box much faster on the 120th iteration. Even when you consider boxes on the X and Y axis with respect to the target box, we reach the box much faster because now we're considering the distance between the centers. And it also has better regression because even though the IOU loss and GIOU loss was the same for the 3 examples that's depicted between the red and green, now since we're considering the distance between the centers, the DIU loss will be different for the 3. That means our model is learning new parameters in order to minimize the DIU loss. But we didn't account for the aspect ratio, which is an important geometric factor. So in order to address that problem, the final type of IOU loss, CIOU loss, was introduced. CIOU stands for Complete IOU Regression, and it incorporates all of the geometric factors. First, we talked about the overlapping area in GIOU. It also counts for the distance in DIOU between the two centers. The one that wasn't covered was the aspect ratio. So in order to compute the CIOU loss, 1 minus IOU is the same as before, as the IOU loss. Then when we added the rho squared divided by c squared term, we accounted for the distance between the centers of the two boxes, which is DIOU loss. Now we add another term, which is alpha multiplied by V, which is going to account for the aspect ratio of the two boxes. And the V term is just 4 divided by pi squared, which is a constant, multiplied by the tan inverse of the width of the ground truth bounding box divided by the height of the ground truth bounding box, minus the tan inverse of the width and height of the predicted bounding box, and we square. It's just we take the angle between, if the green box is the predicted bounding box and the red box is the target box, for the ground truth box, the angle will be between the H and HGT, and for the red box, it will be between W and H. So the angle between H and HGT will be the arctan of WGT and HGT, and the angle between the diagonal of the red box and H will be the arctan of W and H. Next, we're going to talk about non-maximum suppression, which is included in the bag of specials. The normal maximum suppression that we have seen in the previous video was the greedy NMS, and it's the most common and widely used post-processing step. So we used the algorithm let B represent the list of predicted bounding boxes. So if we have a list of bounding boxes in B, we select the bounding box with the maximum confidence score, M, and we store it inside a list of D, and we compute the IOU between M and the remaining boxes in B. So we compute the IOU between the box that has the maximum confidence score and the remaining bounding boxes. Then we delete the boxes whose IOU is greater than the IOU threshold, and we repeat the process until B is empty and D will contain the retained bounding boxes. So on the formula, we can see that the IOU between M and BI, where M represents the box with the highest confidence score and B represents the other bounding boxes. If their IOU is less than the threshold, we save them. And if their IOU is greater than or equal to the IOU threshold, it will be 0. Another type of non-maximum suppression is the soft non-maximum suppression. So the previous one, the greedy NMS, completely removes the boxes which do not satisfy the IOU threshold. So when they are greater than the IOU threshold, we're just giving a value of 0. And this may not be suitable when there are overlapping or crowded regions in the image. So there might be a scenario wherein a box overlapping with the most confident box contains an object of interest, but eventually it gets removed due to the threshold, and this may result in the object not being detected at all. So when we have soft NMS, it slightly modifies the greedy NMS. On the previous one, we have 0 when the IOU was greater than the threshold. But now, the soft NMS proposes a very simple change to the greedy NMS in that it suggests that rather than removing the boxes which do not satisfy the threshold by giving a value of 0, the confidence scores of the boxes should be decayed by an amount proportional to the IOU. So we just multiply SI by 1 minus IOU of the box with the maximum confidence score and the rest of the boxes. We give a very small term instead of giving a value of 0, and it gets penalized by this loss by the 1 minus IOU term. In this way, the boxes having higher IOU are penalized more than the boxes which are farther away with the lower IOU, similar to greedy NMS. So instead of just giving a value of 0, we penalize when the IOU between the bounding box that has a maximum confidence score and the rest of the bounding boxes is greater than the threshold value. Another modification to the soft NMS is finally the DIOU NMS. And when we talked about the DIOU loss, we have seen the term rho squared divided by c squared, which accounts for the distance between the centers of the boxes and the diagonal of the smallest enclosing box. So in this case, when we use the DIOU NMS, when we subtract this term from the IOU and it's less than a constant value epsilon, then we preserve the box. And when this term is greater than or equal to a certain threshold value, we give a value of 0. So the central point distance RDIOU between the two boxes has been shown, which has been shown on the image, is the term that's new in terms of DIOU NMS. And DIOU NMS has been shown to work better in case of occlusions and ensures tighter boxes. So that's all about the techniques that are introduced in YOLOv4. And let's see the influence of the implementation of these techniques during the training procedure. So the influence of the Bag of Freedom and mesh on the CSP Resin X50 classifier accuracy is shown by the table above, and the influence of the Bag of Freebies and the mesh activation function on the CSP darknet classification accuracy is shown by the table at the bottom. And the proposed Bag of Freebies backbone for the classifier training includes the cut mix, mosaic data augmentation, and class label smoothing. So as you can see from the table, when they introduced the cut mix, mosaic, and label smoothing together with the mesh activation function, they got the higher accuracy. And when we see the influence of the Bag of Freebies on the detector training using the MS COCO dataset, the previous one was for classification, and now we're training the detector and implementing the bag of freebies we have discussed. And finally, when we introduce SMIT, GAOA, and CIOU, which we have seen previously, it obtains the highest accuracy for the detector training. And the influence of the bag of the BOS, the bag of selection on detector training. For BOS, the detector gets best performance when using SPP, PAN, and SAM. And we have seen that BOS is modifying the architecture. And when we use SPP, PAN, and spatial attention module, we get the highest accuracy for the detector. So the influence of different backbones and pre-trained weightings on the detector training. So although the classification accuracy of the CSP ResNext 50 models trained with different features is higher compared to CSP.NET 53 models, the CSP.NET 53 model shows higher accuracy in terms of object detection. So we have mentioned previously, when we compare between the CSP ResNext 50 and CSP.NET 53 to be selected as a backbone, we said that the CSP ResNext 50 had the highest accuracy in terms of classification, and the CSP.NET 53 was better in terms of object detection. So using Bag of Freebies and mesh activation function for the CSP ResNext 50 classifier training increases its classification accuracy, but further application of these pre-trained weightings for detector training reduces the detector accuracy. So when they implemented the Bag of Freebies and mesh activation function for the classifier using the CSP ResNext 50, they got higher accuracy for the classification, but lower accuracy for the detector. But when they used the Bag of Freebies and mesh activation function for CSP.NET 53, for the classifier, it increases the accuracy, and also for the detector, it was shown that it increases its classification and detection accuracy. So the CSP.NET 53 was chosen over the CSP ResNext 50 because the improvements have been shown in terms of accuracy, both on the classification task and on the detection task. But for CSP ResNext 50, it increased for the classification task, but when we introduced the Bag of Freebies and mesh activation function for the detection task, the accuracy was lower. Now, this image shows us the comparison of the speed and accuracy of different object detectors using one GPU of either Maxwell, Pascal, or Volta type. So as we see from the figure, with different types of GPU, YOLOv4 are located on the Pareto optimality curve and are superior to the fastest and most accurate detectors in terms of both speed and accuracy. So when we compare the speed and accuracy of different object detectors on the MS COCO dataset, the table on the right shows the frame rate comparison results using the Maxwell GPU only. And there are also tables showing the performance when using the Pascal and Volta GPU. And the real-time detectors with 30 frames per second or higher are highlighted in blue in the image. And YOLOv4 outperforms all of these that are depicted in blue, which have frames per second 30 or higher, such as Efficient Det, ASFF, NAS, FPN, CenterNet, and CornerNet. So it outperforms all of these detector networks in terms of object detection while using the MS COCO dataset. So that's all about YOLO v4.